Today we shall be dealing with digital electronics, a subject which basically entails with how do we convert data from analog to digital, and basically why digital, because in electronics we have two parts. We have analog electronics and then we have digital electronics. So whenever we talk about digital, it means it is anything which can have discrete signals. So we can talk about that in digital electronics we have discrete signals or values. So a discrete value, it means it is either at logic 0, so it means it's either at logic 0 or logic 1. So a signal has been converted from either analog to these values, zeros and ones. So why do we do this one is that most systems which we are available are in digital in nature. Most signals are in analog. So basically, how does our things like mobiles, our personal computers, how they communicate? They use what? Zeros and ones. So even in transmission, we use what? Zeros and ones, which we encode and then we transmit. So basically now we want to do this part of digital electronics so that at least somebody will understand that whenever I'm transmitting these signals in terms of zeros, what happens. So our topic today, basically, we shall be dealing with what we call logic gates. This is our topic today under digital electronics. So a gate, logic gate, as we understand this term gate, is it is something which enables you to somebody to do what? To enter in or to go out. So a logic gate is basically a building block of any device or of any digital system. So it is the simplest building block. It is the basic which is being used to generate or what? To build what? A digital system. Things like what? Our mobiles are made of different logic gates which have been combined together either to form what we call ICs or the large-scale integration. So whenever we talk about large-scale integration, it means that several logic gates have been combined together to form what? A circuit, basically. So a circuit is made of several logic gates. Now, we have the base gates and we have the other gates which can be made from the base gates. So we have three base gates, basically. The base gates which we have are three. We have the NOT gate, we have the OR gate, then we have the NOT gate, OR gate, AND gates. These are our major or the basic ones. Now it means from these ones we can make other gates from them. Like now, if I combine a NOT gate and an OR gate, I get a gate known as both an OR gate. If I combine a NOT gate and an AND gate, I will get another gate known as what? NAND gate. So basically then from there, in part 2 of it, we can have what? Other gates. So we have other gates which are implemented from this. Like now, we can talk about NAND gates, the way you have said. We want to see later that the NAND is made of what? Is made of AND and a NOT gate. Yeah, the output of an AND gate will be inverted. We shall see later. Then we have the NOR gate. We have the NOR gate. Then we have another gate we call exclusive OR. It's a special type of OR gate. Exclusive OR. In simple terms, most people, they refer it with XOR. So whenever you see exclusive OR or XOR, it basically means this gate. And then now, this XOR, we can have now exclusive NOR. Exclusive NOR. It's a special type of what? NOR gate. Exclusive NOR gate. So in bracket, we call it XNOR. So basically, these are now the gates which you have. NOT gate, OR gate, AND gate, NAND gate, NOR gate, exclusive OR gate, and exclusive NOR. All of these gates, we want to realize that sometimes these two gates, the NAND gate and the NOR gate, can be used to implement the other gates which you have seen here. So it means that sometimes we call the NAND gate and the NOR gate universal what? Gates. So sometimes a question might come in. Explain why NAND and the NOR gates are referred to as universal gates. The major point is because we can implement other gates from what? These two gates. And number two, they are also affordable, readily affordable, and they are fast in operation. So after maybe explaining or describing all the gates, now we shall talk about implementing other gates using NAND or NOR gates. So let us start with the first gate. Our first gate is the NOT gate. Now that we have defined them and we have seen how many are they, we talk about a NOT gate. So a NOT gate is a gate which takes only one input and gives you one output. So basically, these gates, the output is the opposite or is the inversion of the input, which means this gate can behave as an inverter. So our NOT gate, the symbol of a NOT gate appears this way. So then we put the input, like now we can say our input is A. So because it inverts, so we say the output Y is equal to A bar. So a NOT gate is basically a gate which takes only one input and gives you one output, but the output is the inversion or is the opposite of the input, which means if here I have 0, then the output, because it's A bar or A invert, we get what? 1. If here I put 1, here we get 0. So our truth table, we can have inputs, then we have output. So our input we can call it A, our output we can call it Y or F, depending on which one you like most. So A can be 0 or 1, because we are said from the definition is that here we talk about what? Zeros and 1s. So if A is 0, because the output Y is the inversion of the other one, or is the opposite of the input. If you have 0 here, then here we have what? 1. If we have 1 here, then here we have 0. So you can see from the truth table that the output of a NOT gate is the opposite of the inputs. And then there is a note here which are supposed to know that the truth is, there is a note here I want you to get out, is that if I have two inputs, two NOT gates, if I have two NOT gates here, another NOT gate here, and then I have the input here, A. So if A, then here it will be A bar, here it will be A bar bar, same as A. Let us prove it is true. If I have 0 here, through this gate, I will get what? 1. 1 invert, we get 0. So it means the output here is same as the input. If I have 1 here, through this gate will be 0. Then through this gate will be 1. So if you are keen now, it means that the inputs pass through two NOT gates, it will be the same. So in simple terms, there is a rule which says that A is same as A bar bar. That two gates, NOT gates, if you put an input through two NOT gates, you will get the same output as the input. So we shall be using it somewhere, like now when we are talking about things like De Morgan's theorems, we shall come under this one, so that now we can be changing a variable, or we can be using it in the Boolean algebra. Now, basically now this is the NOT gate. The next gate which you talk about is the AND gate. Number 2 is the AND gate. AND gate. So to simplify this, we can say that an AND gate is referred to as a series switch in those people who are doing electrical. It's like a series switch. Why we use this is that it is easier for one, when you use this as a switch, to understand better of. Like now, if I draw the circuit diagram, if I have switch 1 there, then you have the potential or the voltage V, which should be applied here. So I have two switches here, and then I have my numb here, somewhere, someplace. I like using this so that people at least will understand clearly or easily. So if I have switch 1 and switch 2, and then I apply power here, and then my y is the number. My y is the number. So let us see what will happen. I can draw now the table of this switch. We see the way it is going to apply. So we have the inputs. We have the outputs. Let us see what will happen. Our inputs now is switch 1 and switch 2. Then our output is the Y, which is our number. Let us see when it will be on and when it will be off. Now, for example, if I apply the voltage here, switch 1 and switch 2, both of them are off. So we can say off, off. It can be, sometimes one is off, this one is on. Then this one is on, this one is off. And then lastly, this one is on, this one is on. Now let us see. Apply the voltage. Switch 1 off, switch 2 off. The truth is there is no power circulating through the circuit, so the ramp will be off. Then again, switch 1 off, switch 2 on. So, sorry, I've drawn the circuit which I've drawn is for the OR gate. Let us deal with the OR gate first. We can change that, we deal with the OR gate, then we come back to AND gate. Because the circuit I've drawn here, since we don't want to change it, is the OR gate. OR gate. Let us deal with OR gate. Then, so the second gate is the OR gate. An OR gate, we call it as a parallel switch. Yes. An OR gate is a parallel switch where that we have two switches, switch 1 and switch 2. And then we can apply the voltage here. We can see what happens there to the ramp. Now, let us start again. Switch 1 off, switch 2 off. You apply V or our voltage. Nothing will happen to the system. Switch 1 off, switch 2 on. Voltage will travel through this to complete the circuit, so our number will be on at this moment. Switch 1 on now, switch 2 off. Switch 1 on, switch 2 off. So what will happen is that power will pass, or voltage will pass through this, and then the ramp will be on again. Two switches in parallel, and then they are on. What will happen in the circuit? Two switches on, these two of them. What will happen is this one will read on, and also at the same time, this one will give us what? So we can say that it will have more light, so it will be on. Now, that's where the problem comes. Like now, when you want to do now, remember when we deal with what? Digital electronics, we say in digital off implies 0, on implies 1. Sometimes some people don't understand when you say that 1 or 1 is equal to 1. So I want you to understand from this parallel switch that 1, 1, it means two switches on. Because now when it comes to the truth table, we are not going to draw this, other than we want to use this to explain what happens when the two switches are what? On at the same time. So if 1, 1, which means two switches on, we can get what? That our number is on. So from there, that's why we say in OR gate that 1, 1, 1, 0 now, 0, 1, and 0, 0. And we want to talk about that, that 0, 0 will be 0, 0, 1 will be 1, 1, 0 will be 1, and 1, 1 will be 1, or will be on. So now, remember, when we do binary arithmetic, 1 plus 1 is 0 carry 1. I want to put that one as a note. But in OR gate, 1 plus 1, or 1, it means two switches are in parallel, and both of them are on. We get a 1 here. I want to now to draw the symbol of an OR gate, sorry. I draw the symbol of the OR gate and the truth table. Then I will compare with what we have drawn down there. We see if they mean the same. So the symbol of the OR gate now, number 2, is we are talking about OR gate. The symbol of the OR gate appears this way. It is like something this way. Then remember I said it's only the NOT gate which takes only one input. So we have A and B. Then our output Y is equal to A plus B. So this expression, later we shall see them, we call them the Boolean expression, which means Y is equal to A plus B. So that's the expression now for the OR gates. So you can get the people saying that with aid of a symbol, Boolean expression, and a truth table, describe an OR gate. So this is the symbol for an OR gate. This is the Boolean expression. What's remaining is a truth table. So I can draw the truth table here. So we have the inputs and then the outputs. So our inputs are A, B, and then we have Y are A plus B. From down here now we can be, I want us to link this, switch 1 and switch 2 off. So our switches now are the inputs A and B. So 0, 0, if A and B are 0, 0, off, off, 0, 1, off, on, 1, 0, on, off, and then 1, 1, on, what will happen? So 0 or 0 will be 0, as we have seen down there. 0 or 1 will be 1. 1 plus 1 will be 1. 1 or 1 plus 1 is 2 switches on, 1. So from here, from the truth table, you can see clear that an OR gate is only and only off when all inputs are absent or are off. So it is always on except when all the inputs are at logic 0 or are off. If any of them or all of them are switched on or they are on, then now we get the output being active. That's an OR gate. The third basic gate is the AND gate. That's the third one. The third one is the AND gate. So let us see what happens with the AND gate again. I will use again the switches or the electrical principles so that people will understand clearly what's happening. So the third gate is the AND gate. AND gate. So the AND gate is a series, another name we can call it is a series switch. I will tell you later why I call it switch this. It means that the switches are in series. Switch 1, maybe switch 2, and then the NAMP. We have the voltage here. Then from there, so we have our voltage, switch 1, switch 2, and then we have our number Y. So that at least people can see clearly. Why do we call it a series switch? So we have the inputs and the outputs. So our inputs are switch 1, switch 2. Our outputs is Y or the NAMP. Some books, they use F. It means the same thing. There's no problem. So then from there now, we have off, 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 on, off, and then on. Now, let us start now. Apply the power. You get your voltage. Switch 1 off, switch 2 off. What will happen to the RAM? Off. Nothing will happen here. Scenario number 2. Switch 1 off, switch 2 on. Switch 1 off, so there is no power. So also switch 2 cannot do anything. So it will be off. Scenario number 3. Apply power. Switch 1 on, switch 2 off. Power will move up to here, but getting the switch 2 is not connected. It will not do anything. So it will be off. Then apply your power here. Switch 1 on, switch 2 on. So power or voltage or current will pass through, then the RAM will be on. Now, so it implies this way, that in an AND gate, power or the voltage or the RAM will be on only and only when all the inputs are on or are switched on or are present. So it implies this way, that this gate will be on and only on when all inputs are present or they are on. Or in the circuit, we're going to say, when all inputs, there's no input with a malfunction. So it will work now. So now, we can draw now the symbol for an AND gate. An AND gate appears this way. Remember, we agreed that it's only one gate which takes only one input. Others can take 2 or more. So now, then we have the inputs. Still, you can call them A and B. Then we have the output here. I can call it still Y is equal to A dot B. So this expression is for AND gate. Remember, for OR gate was Y is equal to A plus B. This is Y is equal to A dot B. It's like a multiplication. That's now in the truth table. You can have a truth table of this gate. Now we have the inputs, and then we have the output. So let us see what happens. A, B. Then we have Y equal to A dot B. Our inputs of 0, 0, 0, 1, 1, 0, 1, 1. 2 switches off. As we have seen from there, it will be off. Off now in digital electronics will be 0. 1 switch off, the other one on. Remember now, A is switch 1, B is what? Switch 2. So if switch 2 is, which is B, represented by B, is on, but the first one is off, still we shall get 0. Then the switch 1 is on, which is A, switch 2 is off, which is B. So still we get 0. But if both of them are on, we get 1. So the other way you can represent this one is A 0.0 will be 0. 0.1 still is what? 0. 1.0 is 0. And 1.1 is 1. It means this way. This gate will be only and only on when all inputs are present. The other OR gate was on when any of the input is present or all of them are present. So the 3 basic gates are basically these ones. We have talked about the NOT gate. We have talked about the OR gate. We have talked about what? The AND gate. So those are the first 3 gates which one should understand in digital electronics before he moves to implement what? The other gates. So once we have understood these 3 gates and their operations, sometimes someone can ask you that represent them using what? 3 inputs. So there's no problem. What you do now, you come here and then you, like now, let me form a question here. I want to form a question here and we represent it, because somebody might be thinking it's only 2 inputs. No, we can use 3 inputs and it's allowed. 4 inputs is allowed. What will be changing are the number of variables in our truth table. So if they say Q, draw a truth table and a symbol of a 3 input AND gate. So what? Remember, we have done the 2 inputs. Now we want to do what? 3 inputs. So what happens is you bring your gate here. You put the variables. There are 3 variables or inputs. You can now go to them A, B, and what? C. Now I want to use F because so that you don't cram what? Y. That I have to use Y everywhere. So I can say now my F is equal to A dot B dot C. Some people write just or A, B, C. It's the same thing. If you see A, B, C or A dot B dot C, it implies the same thing. So now if I have another the 4th input, then it will be A dot B dot C dot D. So it will depend on the number of variables or the number of inputs required in that logic gate. Now what happens is the truth table will change also. The inputs, then we have the output. Now that's a truth table of what? 3 inputs AND gate. So we shall have A, B, C, and then we have F. Some people have a problem with drawing this truth table. I want to give you the simplest way of drawing these tables. Just come here and write what? 4, 2, 1. Now the question is, somebody might be asking, where am I getting these variables from? Basically, because we are using 2 terms, 0 and 1, it means our base in digital electronics, the simplest base we use here is radix 2 or base 2. So 2 power 0 will be 1. Then 2 power 2 will be 2. And then 2 power 1 will be 2. 2 2 power 2 will be, so I'm just getting a power of what? Power of 2 power, the 1, 2 power, sorry, 2 power 0, 2 power 1, 2 power 2. If I have 4 inputs, I go to 2 power 3, I will get 8 here. Now, why am I doing this way? So that it will be easy for me to get this, instead of writing 0, 0, 0 up to the end, and people have some problems, some of them, I just come here. What is here? 4. So 4 are 4 zeros. 1, 2, 3, 4. I'm done with the 4 zeros. So next will be 4 ones. 1, 2, 3, 4. As simple as that. The next is 2. It implies what? 2 zeros followed by 2 ones. But I'm not through. So it means again I repeat. 2 zeros followed by 2 ones. And then next is 1. So 0, 1, 0, 1, 0, 1, 0, 1. And you have your inputs. So you don't need to have trouble in drawing what? A truth table of 3 inputs, because so long as you remember that this symbol rule 4, 2, 1. 4 zeros, 4 ones. 2 zeros, 2 ones. Then the 0, 1, 0, 1 until you reach the end. And we have said from up there that an AND gate is a series switch. It will be on and on when all inputs are on or are present. So it means I get an output here. But all others would be at logic 0. So that is a truth table of a 3 input AND gate and the symbol, or the Boolean, or the symbol for a 3 input AND gate. The Boolean expression now I can say here F is equal to A dot B dot C, or ABC, as simple as that. If this is for OR gate, yes, it will be the same. What will change now is the symbol. So here we have A plus B plus C, and then we the only place where we have it being 0 is here. Others will be what? Ones, as simple as that. So I want us, before we close the session, we do at least 2 gates more, which is the NAND gate and then the NOR gate, so that now when we meet next we do what? XNOR and exclusive OR. But because at least we have understood the first 3 gates, I want us to do 2 more before we call it a day. So I want us to talk about the NAND gate first, then I talk the last one, which is the NOR gate. So as you are seeing from this NAND, it means you AND first, then you negate, or you AND first, then you pass it through a NOT gate. So what will happen is I will get an AND gate. Since I've talked about an AND gate before, I will get an AND gate, A dot B. So our variable will be A dot B. And we have said that for us to obtain an AND gate is the output of AND gate inverted. Inversion means pass through a NOT gate. So I bring a NOT gate here. Bring the NOT gate here. So that now from there, our output Y or F will be A dot B. How was the NOT gate behaving? Inversion. Bar. So we can say in simple terms that the result of passing the output of an AND gate through a NOT gate resulted to a gate referred to as what? NAND gate. So, but this is not the symbol of a NAND gate. I want now to draw the NAND gate symbol, and then I draw the truth table, how it appears. So the NAND gate now will be this way. This will be the symbol with the inputs A and B. So our output Y, we have agreed, is A dot B bar. There should be a negation here, sorry, to show that this is now, we ANDed, then we pass through a NOT gate. So it will be A dot B, which is the AND gate, then negate, carry the symbol of a NAND gate. How is the truth table? We have the inputs and then the output. I draw 2 of them. So I want to draw the first one, which is A dot B, and then A dot B bar. This is the symbol as 0, 0, 0, 1, 1, 0, 1, 1. For easy understanding, we can say since the output of a NAND gate is the opposite of an AND gate, so here it will be 0 because for the AND gate here it was 1, others will be what? Ones. So from there we can see that the NAND gate is off only when all the inputs are present or they are switched on. So if you switch all the inputs on, the NAND gate will be off, since it is the opposite of an AND gate. But I want to draw a truth table which will show clearly what's happening in each. So let me draw the last truth table. We have the inputs, then we have the outputs. So I have A and B as the input. Then I pass it through an AND gate. I get A dot B. But my Y will be equal to A dot B bar. I have drawn two of them so that at least somebody will see. We pass through the AND gate before we obtain the output of an AND gate. So our inputs are 0, 0, 0, 1, 1, 0, and 1, 1. We agree that it's an AND gate is like dot or multiplication. So 0 dot 0 will be 0. 0 dot 1 will be 0 again. 1 dot 0 will be 0. And then 1 dot 1 is 1. Up to there, up this point, this is the output of an AND gate. And from what I do first, I show that the output of the AND gate will be passed through another NOT gate to obtain what? A NAND gate. So what happens is that I have A dot B now, up to here. I have A dot B. Then I will pass these outputs, or I will invert them through the NOT gate. So what will happen? If I pass this output through to NOT gate, 0 will be 1, 0 will be 1 again, 0 will be 1, this one will be 0. Now if you can check from here, you can see why we are on the direct saying that we have 1, 1, 1, 0. But for some to understand it clearly, it's better off we pass through the AND gate. We show that an AND gate gave us A dot B, which is 0, 0, 1. Inverting them, then we get what? 1, 1, 1, 0. So we can see from here that an AND gate will be off only and only when all inputs are present. Like now, if we can go practically, maybe we can say that, for example, if I'm using what? The red, yellow, and so 3-phase. So those are my inputs. So if they are, then there is my machine here, it can be a motor. And my motor will be only on and on when all the inputs are present. If not, then I should have what? An alarm here to indicate there is a problem. Let us see what happens. Maybe now I can connect them through the programmable logic controller to be giving me an alarm, or to indicate that things are okay, the motor will be operating. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. We have agreed that our motor is a 3-phase what? Motor, which means for it to operate, all the 3 red, yellow, and blue phases should be at logic 1, or should be switched on from the one who's generating the power, or providing the power supply to us. So the motor will be on only here. All the situation is here, the motor will be 0. Remember, I've connected via the PLC. So that once there's a problem, or there's a malfunction, as we call it in technical terms, once there's a malfunction, then the alarm should be on. Otherwise, if things are okay, the motor should be running, as we have seen here. But if there's a problem, an alarm should be indicated to indicate that either 1 or 2 of the phases has a malfunction. So it means the motor here will be on here, will be on here, will be on even here, even this place will be on here, 1, 2, 3, 4, 5, 6, 7. But at the moment all of them are on, the alarm should be off, but the motor will be working. In simple terms, now let us come practically. It means for the motor to be working through the PLC, I can have an AND gate, so that once the three phases are on, there is no problem with the motor. But now the NAND gate can indicate that there is a problem with either 1 or 2, so that now we can send our technicians to go and check where there is a malfunction. So we can apply them that way. in most what? In most automated industry organizations. Now, before we stop, the last gate for today, I wanted to go over practical so at least people can be seeing what we are talking about here, so that it cannot just be theory, but it can be applied. So the last one, and before I forget, by the way, these gates are the one which implement what? Programmable logic controllers, the PLCs, which most organizations are using. If you don't understand the logic gates, it will be very difficult to understand how you program the PLCs. Now, the last gate for today is the NOR gate. And as you can see from up there, the NOR gate is made of an OR gate and a NOT gate. So it means the output of an OR gate are inverted to obtain what? The NOT gate. So I would just try to draw to see what happened. Remember, we said the OR gate appears this way. The OR gate appears this way. A, B. So here we have A plus B. But the output of this gate should pass through a NOT gate. So that now our Y, let me use F now. I don't want people to cram just Y. Our F or Q will be equal to A plus B bar. So the output of an OR gate, passing them through a NOT gate, will generate or generated a gate by the name NOR. So NOR is you OR, then you NOT or you invert. So the symbol for this gate appears this way. So this is the symbol. Then you have a negation here. So anybody maybe, if you see that this negation, it means you are inverting. So A and B, it will be now Y is equal to A plus B, but you invert. Now we can draw the truth table for this gate. So we can have the inputs, then the outputs. We have A and B, then we have A plus B but inverted. So 0, 0, 0, 1, 1, 0, 1, 1. An OR gate is a parallel switch. It is off and off only when or the inputs are absent. So it means the opposite of an OR gate is, it means here it will be 1, others will be 0. But because this one does not show me clearly what's happening, I like drawing another truth table passing through the OR gate before I go to. So now, inputs, then outputs. So let us see what happens. This one will show us clearly what's happening here. There we have A, B, then we have A plus B, then we have now our F. We say it is F. Sorry, it should be F. F is equal to A plus B inverted. So let us see what will happen. 0, 0, 0, 1, 1, 0, and 1, 1. Remember, we start with the OR gate. An OR gate is a parallel switch. It does not give us an output when all the inputs are absent. So the only point where this 0 will be here, others will be what? Will be ones. But we have agreed that an OR gate is the output of an OR gate inverted. So this is the output of an OR gate. We invert, we get to what? 1, 0, 0, 0. So if you check here and here is more or less the same. But we like passing through the OR gates so that somebody does not understand the clear digital would see whatever we did under OR gate. If we invert, we get what? The output of a NOR gate. So they resemble each other. If so they talk about 3 inputs, you add here to be A, B, and what? And the C. Then now the variables will be 3 of them until you get to what? 1, 1, 1. Then the truth table will be the same. Here the symbol we should have 3 inputs, maybe A, B, and what? And C. So that now the Boolean expression will be Y is equal to A plus B plus C inverted. As simple as that. So basically today, before we finish, we're going to do a recap. We have talked about how many gates? We have talked about the NOT gate, which we refer as an inverter. We have seen that the output of a NOT gate is the opposite of the input, or is the inversion. You invert the inputs to get the output of a NOT gate. After that, again, we realize that this is the only gate which takes only one input. Then we have talked about the second gate, which is the OR gate. We referred as a parallel switch. We saw through the switch what was happening. We realized that this gate will be off only and only when all the switches are at logic 0 or they are off. So that's why we are referring as a parallel switch. We talk about the AND gate, another gate there, which we realize that this gate will be on and on when all the inputs are at logic 1 or they are present. We have talked about that, or we have realized that through the AND gate and a NOT gate, we can have other gates, which we are talking about 2 of them. The first one, we're talking about the NAND gate. And we have realized that the NAND gate is made of the output of an AND gate. To pass it through the NOT gate, we obtain the NAND gate. So NAND means and NOT gate. So it gave us a gate by the name NAND gate. And I've shown you the application of what? NAND and AND. Then lastly, we have talked about the last gate, which is what? NOR gate. NOR gate we have here also as the NAND gate. It is made of 2 gates, which is the OR gate and the AND gate. And we realize that the output of the OR gate pass it through a NOT gate will generate a gate known as what? A NOR gate. And we have realized that if you have the output of an OR gate from here, this is the output of arrow through the truth table. Invert, you get the output of a NOR gate. So there are 2 more gates remaining, which is the exclusive OR gate and the exclusive NOR gate. Then from there, we can see in case you have only one input and you have a NAND gate, what will happen? So we should also try to show you how you implement. If you have only one, if I have a NOT gate, I want to implement using a NAND gate. And we have agreed in our learning that NAND gate will take 2 or more inputs. How do you connect that one? How do you jump the wires so that you obtain what? You can use a NAND gate to obtain a NOT gate. Then when we meet in the next lesson, we shall see what's happening there. And then remember, these gates, maybe that's why I would finish that, these gates are made of ICs. So they are available in the market. And they are made of what? ICs. So I wish to thank you because of listening, and I hope that you have understood what we have done today. When we shall meet next, we shall see these 2 remaining gates. Then we shall connect these gates. We see how we obtain the outputs. When we talk about combinational logic circuits, how do you obtain the outputs from there? It is an interesting subject, this is electronics, because we are going to basically do what? Zeros and ones, and we are going to do it what's practicable or what we do day in, day out. How are our circuits, our devices connected? How are they implemented? How are they working or their functionality? Thank you for today. Let us meet the next lesson, which I think should be tomorrow.